Right. So again, thank you, Liana, for organizing this and for inviting me. Right. So I'll be talking about joint work with Jung-Kyung Lee and Alexei Pokrovsky, who are both my colleagues at UCL, at least for the moment. And I'll be talking about Chi-boundedness of graphs with no cycle with K chords. So to begin with, we want to talk about Chi-boundedness. And for this, there are two graph parameters that we should talk about. So I presume you all know that the clique number of a graph G, which I normally denote by omega of G, is the size of the largest clique in G. For example, here you have a graph and the largest clique is, has size 4. So the clique number is 4. So presumably you all know that. And also we want to talk about the chromatic number. So this is the minimum number of colors in a proper coloring of the vertices. And by proper coloring, I mean that adjacent vertices have different colors. So here's an example of a proper coloring of the graph G. Right. Okay, so I guess one of the first things that one may notice or learn when they talk about these two parameters is that there is some relation between them, namely that the chromatic number always has to be at least as large as the clique number. And the proof is essentially this picture. Like, let's look at this clique. Because my coloring, because of any proper coloring has to give different colors to each of the vertices in the clique, then it has to use at least the number of vertices in the clique, many vertices, right? So this shows that for every graph G, the number of colors in a proper coloring is at least the number of colors in the largest clique. So we have this inequality. However, like any kind of attempt at the reverse inequality will fail. So any attempt at saying the chromatic number is at most like omega G to the 1000, that's going to fail because this is like a kind of nice but maybe a bit challenging exercise for students. One can explicitly construct a family of graphs that are triangle free. So triangle free in particular implies that the clique number is, well, 2, or at most 2, I guess, and whose chromatic number is as large as you like, right? So this gives us a family of graphs whose clique number is bounded, is at most 2, but chromatic number is as large as we like. And so any hope of bounding the chromatic number in terms of the clique number is going to fail. Right. So what do we do now? Well, what Piarfa suggested is to basically investigate when the opposite is not, well, when the opposite is true in a sense. So he came up with the following definition. So he called a class of graph curly G chi-bounded if there is a function f such that for every graph in my class, the chromatic number of G is at most f of the clique number. Right, so for me, a class of graphs is just a family of graphs that is closed under taking induced subgraphs. Right, and chi-bounded again means that I can get a sort of reverse of this inequality. So maybe like chi of G is not at most like the clique number, but it's at most a function of the clique number. Right, so this is the kind of definition that started the whole whole research topic. Right. So maybe let's start with the sort of most obvious class of graphs and see what we can say about that. So I claim that this is the most obvious class of graphs. So given a graph H, let's look at a family of graphs that do not have an induced copy of my graph H. right? And we can say quite easily a few things about this. So for example, if I start with a graph H that contains a cycle, then this form of H is not chi-bounded. And the reason for that is very similar to what we had in the previous slide. This is like a famous result of Erdős, one of the first uses of the probabilistic method. And what it says is that there are graphs whose chromatic number and whose girths are arbitrarily large. So here girth means the length of the shortest cycle. Right. So again, this tells me that I can have chi as large as I like, and I can also have like avoid short cycles. So basically, let's say if H contains, let's say H contains a C5, then I'm going to can find graphs with no C5 or like C4, C3, and also chi is large. Right. So no C5 means that I don't have a copy of my H because I don't have even the smaller subgraph of H. And chi is large, well, means that chi is not bounded. And moreover, because again, I can also avoid like triangles, then my clique number is bounded. So again, clique number is bounded. I lie in this family and my chi is large. So to summarize, for this family, I cannot bound the chromatic number in terms of the clique number. Okay, now I do this maneuver. Right. So this told me that if I have a cycle, it's kind of hopeless. So I need to investigate some things that do not have a cycle. And here's an example. Let's look at the star. So for example, here is S3. Right. So I claim that form of Sk is chi-bounded for every k. And let's see why that's true. Right. So I start with a graph which lies in this family. So it doesn't have an induced copy of the star. And I just focus on some vertex of it. And here I drew its neighborhood. And I claim the following, that this neighborhood does not have a clique of size omega of g, nor does it have an independent set of size k. Suppose it did have this clique of size omega of g, then together with the vertex u, I get a larger clique. 1 second. Right, so again, suppose I had my clique, then together with you, I got a clique that is too large. Like my graph does not contain cliques of size omega of g plus 1. Right, and now imagine that it had, my neighborhood had an independent set of size k, then similar thing. If I look at this independent set plus u, then I get exactly an induced copy of my star, which is forbidden because G lies in this family that forbids induced copies of the star. Right. Putting these two things together, the neighborhood of U has size at most Ramsey number of a clique of size omega of G and a clique of size K. Right. So in other words, the neighborhood of U cannot be very large. And then whenever we have a bound on the maximum degree, then we also automatically get a bound on the chromatic number by just coloring greedily, I guess. So in summarize, what we got is that the chromatic number of G is at most this function, which is very large, but is still a function of omega of G and of k, but k is like fixed for this problem. So we think of this as a function of omega of g. So we managed to show that the chromatic number is bounded in terms of the clique number for this family. Right, so this shows us that forb of a star is chi-bounded. Okay, and here's another result which I will not prove. Due to Gerfa, she showed that if we forbid a path on some number of vertices, then we again get a family which is chi-bounded. And this is like not so easy to prove, and has like Gerfa has quite a nice proof for this. Right. So here's again what we know so far about chi-boundedness of this family forb of H. We know that if H is a path or a star, then we are chi-bounded. Otherwise, if H contains a cycle, we're not chi-bounded. So the natural conclusion is that we claim is that forb of H is chi-bounded exactly whenever H is a forest. And notice that so one of the directions is already proved by this statement, so we only have the opposite direction, namely to prove this conjecture, we need to prove that forb of H is chi-bounded whenever H is a forest. And this turns out to be equivalent to showing that forb of T is chi-bounded for every tree T. Right. So this is very much open. Some things are known, probably many more things that I will put in the slide. But here is one thing. So when T is a tree of radius at most 3, then indeed this family is chi-bounded. And I want to state another kind of result towards this conjecture, but for that I need another definition. So forb star of H is the family of graphs that do not contain an induced copy of a subdivision of H. So here is what I mean by subdivision. If this is my graph H on the right, then a subdivision of H is obtained by just putting some vertices on the edges. Right, so I fix my graph H, and I do not allow induced copies of anything that looks like this. And then we get this very nice result by Alex Scott, which says that forb star of T is chi-bounded for every tree T. So it's kind of in the spirit of this conjecture, and maybe like the most general result in this conjecture, I'm not sure. Right. And it also, I guess I just mentioned that it kind of raises the question, well, when is forb star of H chi-bounded? And there isn't, as far as I know, or from the little research that I did, it's not so clear what the answer should be. So behaves a bit different from this forb of H. Right, so now we get to the topic of my talk more precisely. So here's the definition. Curtis C sub k is the family of graphs that do not contain a cycle with exactly k chords. So let me explain. A cycle, well, a chord in a cycle is something like this blue edge. So I have my cycle, and any edge between two vertices of the cycle that is not on the cycle itself is a chord. So this picture has a cycle with 3 chords. Right, and the conjecture that I would like to address is the following conjecture due to Aboulker and Bousquet. It says that this family is chi-bounded for every k. Right, so to give you a little motivation how this relates to the previous slides and why this might be interesting, well, it's kind of a bit of a mixture between this forb of H and forb star of H, because if I have my cycle with 3 chords, then I can start subdividing the edges of the cycle and I still get my cycle with 3 chords. However, if I do the same to the chords, then I get something different. So I'm sort of allowed to subdivide, but only some of the edges. So it's a bit similar to what we had before. Right. So here is what was known. This kind of came before the conjecture, and I guess their motivation was just to investigate the structure of graphs that do not contain a cycle with one chord. And Aboulker and Bousquet proved their conjecture for k equals 2 and 3. And our contribution is the following. We proved that this family curly C sub k is chi-bounded for every large enough k. Right. Okay, so I'll say some things about the proof. We'll see how far we can get. So just to remind you, or to kind of state what we want to do in a different way, our task is to show that if my chromatic number is much, much larger than the clique number n and k, then I can find my cycle with exactly k chords. That's the task. Right. Okay, I don't know if like somebody just, if somebody just stared at this for the first time, I'm not sure it would be clear where to start from, but luckily we had a kind of starting point, which is the following. So it says that for every k and L, there exists a function such that if the chromatic number is larger than this function of the clique number, in other words, again, the setup, like the chromatic number is much, much larger than the clique number and then these k and L, then my graph is guaranteed to contain either an induced complete bipartite graph, induced KLL, or it contains a cycle with exactly k chords. Right, so again, if my chromatic number is way larger than all the other things that I'm looking at, then I'll find a large induced complete bipartite, or I already find my cycle with k chords and I'm happy. Okay, so this was kind of this is kind of a variant of a result by Bousquet and Thomasse, which I won't go into detail about what I do. And yeah, let's say when he suggested to start this project, and he kind of noticed that there probably is this connection, and indeed we managed to prove it by using their method. So anyway, we have the starting point that basically says that we can assume that there is an induced complete bipartite. Okay, now why is this a useful thing to have? Well, let's start with just a naive argument. So I have my complete bipartite graph here, and I just take a cycle in it. So I take a cycle of length 2a, and let's just count the number of chords in the cycle. So in total, the number of edges induced by the cycle is a squared, because this KLL is like induced, right? So the number of edges is just all the edges between the two sides, which is a squared. And the number of edges in my cycle C is 2a, so the number of chords is a squared minus 2a. So if it so happens that my k is exactly of this form, a squared minus 2a, for an integer a, then I'm done. I found my cycle with k chords using this theorem. Right. So obviously not all the positive integers are of this form, but at least that already gives us some hope that we can do something, because right, we at least proved our result, or our we managed to reach our goal for some numbers k. Right, but obviously for a different k, we need to do something a bit more sophisticated. And this something would essentially involve, well, not just the one complete bipartite graph, but many. So I won't explain this, but basically it's not too hard to kind of iterate this theorem to show that we can get not one induced copy of KLL, but many, as many as I like, induced copies of KLL. Right, so basically this corollary tells me either I find my cycle with k chords and I'm happy, or I find many disjoint induced KLLs which have no edges between them. Right, so my plan is to have these complete bipartite graphs and to sort of chain them up. Okay. Right. So let's see how one might connect things up in this world. So the idea is as follows, using this thing called unimodal paths. So the idea, this is a kind of standard idea in this study of Chi-boundedness. So I'm going to start with my graph G, which has massive chromatic number. I look at a vertex U, and I just kind of expand its neighborhood. So this is the vertices at distance 1, vertices at distance 2, etc. Now here is a kind of easy inequality. It says that the chromatic number of G is at most the maximum chromatic number of these red sets. So vertices at okay, I guess this part at distance 3, etc. And the maximum of these blobs of blue vertices that are at even distance from you. So the reason is if I can color each of these red blobs by 10 colors, then I can simultaneously color them by red colors because there are no edges between them. Same with blue. Anyway, moral of the story is that there exists an I such that the chromatic number of this ith neighborhood of U is at least as large as half times the chromatic number of the whole graph. And since this is massive, then this is also massive. Right. So imagine this is my blob with pretty large chromatic number. Then I'm going to kind of focus on this now. And what I can do is basically this. Whenever I take two vertices in my blob that I chose to focus in, my green blob, then I can connect them in this nice way. So I claim that I can connect them using an induced path whose interior lives here. And actually I need a bit more. I need that. The only vertices that can send edges back to here are these, but never mind. Anyway, point is I kind of look at my X, look at my Y. I know that there is a path from X to U. I know that there is a path from Y to U. And okay, maybe some of it intersects. So I'm going to remove it. Maybe there's an edge here, then I can kind of do a shortcut, but it should be quite easy to get my induced path. And this is a very useful way of connecting things in these graphs with large chromatic number. Right, but I will want to connect not just two vertices, X and Y, but I will want to connect various pairs of things. So for that, I'm going to, I guess I should say that a path like this is called a unimodal path. Right, but I will want to connect not just one pair of vertices, but many, and for that, I'm going to want to just iterate this idea. So I'm kind of short on time and I want to get to the next slide. So I'm just going to do this very quickly. So I'm just going to iterate to do this unimodal thing many times. And that will allow me to have many ways of connecting a certain pair in such a way that there is sort of not that much interaction between the various ways to connect. Okay. Right. So here is my big slide that combines kind of everything to a proof. Right. So I know from a few slides back that I can assume that I have many disjoint complete bipartite graphs that have no edges between them. So here they are. And I want to use them to make a cycle. So my first step is to take a path pi of length to ai in, well, the ith complete bipartite graph. So I drew a few here. Right, and now I want to connect them. So I'm going to connect them via these unimodal paths. And because I iterated, then I can take them to be kind of not interacting too much. And by not interacting too much, what we prove is that we can assume that there are O of square root k chords here. So there might be some edges, going here, but just not so many. I mean, remember that I'm aiming at k chords, so O of square root k doesn't matter so much. Right. Now, by some, okay, so something that I didn't really stress was that the only edges that can go from the light blue to the light red are these vertices, well, touching these vertices in this blue strip. And using a Ramsey argument, I can assume that for every vertex here and every part here, either the vertex is fully connected to the part or, well, fully disconnected. So I get something like this. A vertex either sends edges to all of this part or to none of it, maybe with the exception of these connecting edges. Right. And then what I do is take this cycle, count how many chords there are. Right. So I claim I get something like this. I'll just go through this expression, I guess, and finish. Right. So how do we count the number of chords? Well, there are some chords in the light blue, but they're only O of squared K. So this comes from here. Now I need to count the number of chords in the light red. Well, there are no edges between these guys. That's how we set it up. There are no edges here. So the only edges come from like within here, and this will give something that looks like this, I think, or something like that. And then there are these edges between vertices here and parts here, which contribute some factor of AI for each AI. Right. And the main important thing here is that this sigma I and this error term, they don't depend on AI. So I get this expression for the number of chords, but I'm actually free to choose my AI. And I can basically do that to get the number of chords that I want. So I'll put this here, but I guess I need to finish. So
it's
right?
okay, Shoham. We have 10 more minutes till the next talk, so you can.
I thought 5, but
yeah,
okay.
but it's fine. I think.
Okay, thanks.
Take more.
So, right, sorry. So maybe I shouldn't have rushed as much. Anyway, we get this many chords, and we want this thing to be equal to K. Right, so now comes some not very difficult number theory. So you may remember this 4-square theorem, which says that every positive integer can be written as the sum of at most 4 squares. And this is sort of very similar to what we need, but we need something slightly stronger. So one thing that we prove is that every large enough number can be written as a sum of exactly 20 squares, where each of the squares is large as you want. And we also get this similar looking result for instead of trying to express things as sum of squares, we want to express things as sum of AI squared plus AI. But here we have this divisibility issue, right? Each of these guys, like this thing, is even if if sigma I is odd for, no, if it's not even for at least 20 values, then it's odd for at least 80, and then we apply the second lemma with the caveat that we cannot quite get K chords, we can get close to K chords. So to get exactly K chords, we need to do quite a lot of work, which is, yeah, it requires these gadgets and is a bit less fun than what I did so far. So, right, I think I'll finish here.
Okay, thank you. Okay, let me first count to 3, and we can all give Shoham an applause. 1, 2, 3. questions?
I have a question. Two questions. One is about some explicit example for when this what you called C star of a graph, or
Yeah.
was it? I don't remember. Is there an example for
Yeah,
for a clique of certain size,
I'll just put
subdivisions of a clique?
here. I honestly don't remember, but I know that Alex Scott had a conjecture that it should be chi-bounded for every graph age, and this was this. Yeah, I mean, I guess like the obvious. So previously we said though for cycle, I mean, without the star, without the subdivision, if you have a cycle, then it's kind of trivial and that it's not chi-bounded. Here, if you have a cycle, then then every cycle is a subdivision of a small cycle. So it's kind of just very different. Yeah, I don't know. I guess, yeah, I assume it's hard. I don't know if he thought very hard about this conjecture when he posed it, but yeah, I don't think it's clear, like there is a clear conjecture for what it should be.
Okay, and the other question is about chordal graphs. I vaguely remember that maybe even Nicolas Bousquet asked me this or told me about this question at roughly the same time as they posed this question. So are chordal graphs chi-bounded or not? Or maybe I'm confused.
The chordal graph is?
I think a graph in which every cycle has a chord.
They are perfect, Andre. They are perfect. Chordal graphs are perfect.
Okay, so maybe I'm confusing something. I'm saying something stupid. Okay, so then never mind. Sorry.
Yeah, I wouldn't be able to tell anyway. So thank you.
Any more questions? Okay, if not, let's thank Shoham again. Thank you.